All right, cool. So welcome back. I did get that test graded and the solutions are up on Blackboard. Happy to talk about any questions you have about them. I also found a way to attach my solutions to the Gradescope feedback as well. So there's a couple places to check those out. Overall, everyone did a nice job. I provided that review or the reference material, and you had a note card, and maybe in retrospect, you didn't even need that because it was a really, really nice job overall. So I'm happy to field some questions about that if you have it, but I know maybe you need some time to look at that. So let me know. Keep in mind, there's also a couple homework assignments due on Wednesday, like there always are. And we're starting to get into a little piece of the course where we're learning about some derivative rules. And so in order to practice them and have enough practice to get good at it, there ends up being a decent number of problems compared to what we've seen in the past. Especially, I think this week, especially, there's 20 problems in one of the sets, but it should go fairly quickly given what we're going to learn. So just keep that in mind, that the number of problems is going to kind of go up a little bit, but in theory, it's because they're kind of quicker in some sense. But anyway, we'll look into that. And we'll be in person on Friday. We'll have a quiz on Friday like we always do. Don't really think there's anything else I want to say. Questions about anything before we get started? I don't know if you've had a chance to look at the quiz or the other things you want to talk about. More questions at all? So, we're learning about the limit derivative or the limit definition of the derivative, but that's what we've been learning about. We kind of did it at the end of last week, Wednesday-ish, and we're going to finish with that this week. And that is usually something that people find kind of tricky. And we're going to start with a couple examples this week. But I guess what I'm trying to say is when you come upon some homework questions, and maybe Wednesday will be more of a homework day, we can look at some of those in class. Is what I'm just looking back at some of my past notes from the last class, and I did a lot of these in class, but I usually let people drive those questions. So I'll just see if there are questions again right now. If not, we can look at it again on Wednesday. Anything right now? Okay. Give me 1 second. Someone's knocking at my door. Sorry about that. Two-year-old's just knocking on the door. I'm not really thinking about what's going on. Okay, so let me switch back over to the notes and remind us where we were last Wednesday. So we were learning about this limit definition. This is kind of what we left off with, right? That right there. And what we had finished with, I think, was some examples there. So here's the thing that this is kind of like a big summarizing thing, right? These three limit definitions are what's in the homework this Wednesday. That's the formal definition of a derivative using limits. Okay, and there's three versions of them. And so what I'm going to start with right now, and we did an example here, and an example, we found that when we had this function x squared plus 1, we did the derivative using that new formula, and we found out that it ended up being 2x. Right, and so what I want to start with is sort of summarizing what we did. So let me just remind you too that there's three different versions of it, right? The first two, or maybe the first and the third one, have a b in it. Let me go ahead and highlight that here. Right, this one has a b in it, and this one has a b in it. And so those two things were telling us numerical values for the instantaneous rate of change, whereas the middle version, the f prime of x, that has an x in it, and so it's going to be a function, right? And so ultimately what we want to do is be able to measure the rate of change at different points. And so what I want to start with is thinking about how we can do that in these three different ways. And I think I'll sneak that in right at the top here. So what I want to just kind of start with is thinking about, because you see a question a lot something like, what is the derivative at the point 12 or something like that? Doesn't matter what the point is, but f prime of 12, that's like the f prime of b situation, right? And so that's a numeric value. And so we have basically three options in order to calculate the derivative at a point. One of those options is to just plug 12 into f prime equals 2x from last time. When I say last time, I mean last Wednesday. So this thing right here. Right. So if we want f prime of 12, we want the derivative at a specific point. The nice thing about having the function is we can just plug any number into that function to get an answer. And so that's one of the options of what we can do to find the derivative specifically at 12. And that's the easiest thing we can do. If we have a function that tells us the derivative, we can just do that. The other two options are to use the limit definition. So 2 and 3, I would say, are to use one of the following. Right, so I'm just writing down the three things I showed you just a second ago, but specifically applied to this case. And so those are the three options. We either take the function we calculated last time, which was just 2x, and we can plug any number into that to figure out the instantaneous rate of change in this particular function. Or we can do more work, but we can still use one of these limit definitions, right? Either this thing or this thing, to find it, to sort of calculate at that specific point. And I'll slide back to this second, but I'm just trying to lay out these three things again, right? These three things I'm just highlighting that I highlighted a second ago. I'm just sort of saying, here are our three options again, since it's been a week or so since we saw this. And I'm going to look at each one of those separately. And this is the kind of thing that's in the homework too. So that's one of the reasons I wanted to talk about it. Just get us back in gear with this stuff. And so I have another page here. I think this is where you had to insert your own pages. So you should have a blank page, and we're going to do each one of these three things together. And then I'm going to ask you to think about one of them on your own. Are there questions about what I've said so far, what we're looking at here? Oops, just saw the chat here. So on page 22. Yeah, so what I had done was page 22, this is the bottom of page 22. And then what I did is I stuck a blank page in between there that I don't think I had included in your notes. So you will need a blank sheet of paper for this next thing. Yeah, other thoughts? Thank you for those who filled in that blank. Okay, so again, last time, I know sometimes I get to this in the same class, and this is unfortunate, it's been a little bit of time, but previously what we have done, I'll just outline it again. We had the function x squared plus 1, and we found that the derivative was 2x, right? And so that was really, really nice, because if we just know the derivative is 2x, we can plug any number into that to get the rate of change, right? And so let's start by rewriting down what we have. So f of x is x squared plus 1. That implied that the derivative was 2x. That's what we saw previously. And so if we want to know the rate of change at 12 specifically, that's really what we're focusing on right here, is this f prime of 12 is what we want. Then this function just lets us plug anything into that to find it. So the derivative is 2x. That implies if we want the derivative at 12, we just plug a 12 into there. Right, so you can see why having the derivative as a function is nice, because we don't have to do any limits. We just do the limit one time, then we have a function, and then we can plug any number into that function. That's much easier than just doing a limit at every single point that we want the derivative, right? That's sort of one of the things I'm trying to get across here. Is that first one okay? People see what I'm saying there about just plugging the number in to get the value of the derivative? All right, let's remind ourselves about the other two options. So the other two things I've circled in yellow there are the other two things we could do. And so I'm going to split this page just in half down the middle. I suggest you also just split the page in half because we're going to do, oops, the other two things down here. And I would actually try to leave some space at the bottom because I'm going to leave, or you could just get another piece of paper. What I'm going to do is I'm going to leave some space for an example for you to work on yourself or in groups maybe. Although I don't think, still haven't figured out how to do breakout rooms, unfortunately. So, okay. So let's do options 2 and 3 right here. So option 2, right, we're going to do this one down here is sort of the idea. And then we're going to do this one over here. Okay. So the second option would be this limit. Right, this is one version of f prime of 12. The one on the left up top there, right? And let's just go ahead and write down the other one. The third option could be the h going to 0, 1. Right, this is a third option for the derivative at 12. So this is sort of what we're thinking through right now. And I just wanted to write them down both together before we worked on it, so we can just emphasize again that we're doing the same thing here, right? We're just calculating the derivative at 12. So we're going to get the same answer, and we already know the answer is 24. And so we're going to get the answer 24, but just kind of showing you the 3 different ways and the 3 different formulations to get there. And they look different, right? And if you're not familiar with this stuff, they look very, very different. And so it might just be helpful, I thought, to kind of put them all together on one page right here. Is this okay? You guys remember how to do this? Are there questions about the notation? It's mostly a notation thing that people usually get confused by. It's okay so far? And if you haven't looked at this homework yet, you might be particularly confused, but let me just remind you, if I go back to the definition, I tried to lay out these things in the definition, right? Way back here in the definition, right here. Right, so when you look at this definition, I tried to say like, oh, f of x is just a function, right? F of b is the function with something plugged into it. So anyway, just trying to point out that when you go and work on this in the homework, going back to this original page with the definition, I tried to explain exactly what those things are, right? And then we spent a lot of time in the last class thinking about like the f of x plus h part, right? This whole page was like, what is f of x plus h, and trying to think about that, right? So we do have a bunch of tools and a bunch of notes for this stuff. It's just been a little while since we've seen it. All right, I'm mostly stalling there and see if there are questions. Seems okay? All right, so let's write this down. So, right, so f of x is just the function. So the function here is just x squared plus 1. F of 12 is plugging 12 into that function, right? So that would be 12 squared plus 1. And then we just have x minus 12 on the bottom. Right, so here's my f of x. Here's my f of 12. And this is function notation, right? F of x is the function with x in there. F of 12 is the function with a 12 in there. Just following the instructions, basically, right? And then at this point, it's just a limit, and so we're just going to simplify things. This one looks like it's going to be a factor and cancel one. And so at this point, it's just using material we've already seen. So is this part okay? That's all right. Okay, so let's just finish it off then, right? It shouldn't be that bad. Everyone did pretty well in this part in the test. So we know how to just move forward with it, right? So we still have the limit, and then we're just going to simplify. So this is going to be x squared plus 1, and then 12 squared plus 1 is 145, so minus 145. We just do that subtraction. plus 1 minus 145 is minus 144. Right, this is indeterminate, just to be clear. I hope it's not a surprise, but these never work out, right? We get 0 over 0 so far, and so we need to use the techniques that we just had the test on. And as I mentioned, we just want to factor and cancel. And so we know that we just factor this. The denominator is gonna cancel, right? We want to cancel out the x minus 12, so that tells me one thing in the top is going to be x minus 12. That helps me realize it's x plus 12, right? 12 times 12 is 144. In other words, those things cancel and we get our answer. Right, so this is why we obviously learned about limits in the first section so that we can take derivatives, right? And we got the same thing we got previously, right? 24, we already knew it was going to be 24, but we just done it a second way. Let's pause there and see if anyone has a question so far. Just trying to see if I can turn on. Trying to turn on breakout rooms. I have to keep saying I have to do that later, and then I never remember. So I'll make myself a note real quick. Questions? Is that okay? Again, the notation thing. Usually it's this part that people are confused by. Like this, just this first part. That seems okay. All right. So then the second one, again, remember, this is the tricky part of the second one, the 12 plus h thing, right? What are you doing there? That's usually what people get tripped up on. So let's really focus in on that in the second one. So let's start plugging stuff in. So this is going to be the limit as h goes to 0. F of 12 plus h looks like this. Right, that's f of 12 plus h. Everyone make sure that that looks okay. Right, this part is right here. Is that right? Take out the x, put in the 12 plus h. So it gets squared because that's where the x was. And then the plus 1's just coming along for the ride. Is that right? And you'll recall very simple things or similar things happen as the other one, right? Things cancel. You just do some algebra and you just carefully get to the same answer. So let's just write down that answer real quick. When you square out 12 plus h, you get 144 plus 24h plus h squared. And then lots of nice things happen. Let's just simplify the top first, I guess. So we'll have 144 plus 24h plus h squared plus 144, or minus 144, excuse me. We need that 144 to cancel. All right, so the 144s go away, and then the h's are going to cancel, and then we get the answer 24 again. Right, that's the general idea. So let's finish it off. We want to cancel out the h, so we factor it out. H's cancel. And we are just about at our answer. So we got the answer 24, 3 different ways, right?
Could you go down like just a little bit? Because I can't see the, thank you.
Okay, maybe I can turn breakout rooms on. Okay. I don't know if that's gonna like apply right here, but I did just turn breakout rooms on. Probably have to do it next time. There's some questions about this. Again, I'm gonna give you one to try. Are people confused about what we're up to? Kind of the difference between these three things, plugging stuff in, algebra, the limits, anything there? All right, let me give you one to try then. So, and I think this one's from the homework, which is one of the reasons I wanted to do this in class. It's one of the trickier ones. So let's pick this function. F of x is 1 over x, and so it's a fraction, right? Let's find the derivative, and let's use, just so we're all doing the same thing, let's use the h going to 0, 1. And we can, again, if I had breakout rooms, I had done this ahead of time, if I had thought about this, would break us up and let us think about it together. But let's just do it together sort of in stages. Like take a second and see if you can do this first part, right? Can you write down that first expression? What does that look like? This is really helpful to think about. And then, and if if you feel comfortable with this, just roll with it. But if you're sort of iffy on this, you're not sure what to do, let's take in steps. So let's take a second and think about this expression, right? Write that expression down. And I'm going to sort of do it slowly. But by this point, I really think looking at the past notes, you should be able to write that down. So I'm going to slowly do it. You should do it too. So the limit as h goes to 0. Just going to write like this real quick. Let me just pause actually. So give everyone a chance to think about that real quick. What does the numerator look like? So I just wrote down the h part. So all I've done is just copied that part over. What does the numerator look like there? So it looks like, it should look like this. What do you think about that? Let me move it out of the way here so we can see it a little better. So okay, I can do details on this part if you want. Does anyone want to see me do this part? This is f of x plus h.
Yes, I'd like to see you do that.
So let's write down f of x. I always do the same thing, and I hope it's not annoying, but if that's f of x, right? Anytime you plug something in, you just take the x out, and whatever we write into the one spot, we put in the other spot, right? So if it's a number, we put it in there, right? If it's a different variable, we put it in there. And maybe I'll just also just sort of mention, this is the blank spot where the x used to be, right? And just sort of just took it out. And it's a notation thing. And so if this makes sense, plugging in a 1, for example, it goes in both spots, then anything you put in the one parenthesis goes in the other one. So f of x plus h is just this then. And it goes for any function, right? Anytime you plug something in, you should think about just erasing the x, wherever that happens to be, and whatever goes in this spot goes in the other spot. Does that clarify it? I'm not sure. Is that helpful?
Yeah, can I see where you did that in the problem before? So,
Yeah, so on the one before, let me do it here again. We had a different function, but it was the same idea, right? Our f of x was x squared plus 1. So let me write f of blank again. Right? Is that okay? F of blank.
Yep.
And so we can plug a number in there. We plugged 12 in there, for example, right? That was f of 12. That's why it looked like that. That was this piece. And so we can do anything, right? X plus h, for example. That's why it becomes this.
all right, that's good. We can keep going.
Oh, and it was, I'm sorry, it was 12 plus h in that last one. It wasn't an x. So 12 plus h then would be just the same idea, but just 12 plus h. Other thoughts about that at all before I'm going to erase that and we'll keep going with this current one? Oops. So this equals 0 over 0 currently, just to be clear. It's always going to be indeterminate in this stage. And so what technique do we want to try, though? What does this look like to people, you think? Not a conjugate one, because there's no square roots, right? It's not like an infinite limit, so it's not going to be the horizontal asymptote thing or anything like that. What is it? What do people think about? I see
Combined
this.
terms.
You have to make the denominators the same.
Yeah, I think we should combine them. Yeah, right. So this is a combine and simplify. And not sure who said that, maybe Marina, but that means we want a common denominator, that means, right? So the common denominator in this case would look like this. I'm going to kind of write this out carefully in case you're still a little fraction phobic. Do it in red. So if we want a common denominator, we do this one times x over x, and we do this one times x plus h over x plus h. Let me be very clear about something, though, because I'm sure someone is trying to think about this. And actually, I meant to let you try that yourself, and I totally forgot. Oftentimes, people think, oh, well, this one, they both have an x already. We just need to give this one a plus h, right? And then they'll be the same. That's like a very common thing that people think. But the only way you can add to a fraction is by multiplying. So you can't just do like times plus h times plus h or something like that. Because if you multiplied 1 times h and x times h, you'll get x times h in the bottom, right? So you're only, in other words, you're only allowed to multiply, so you can't just stick a plus in there. That's why you need to multiply by each one on either side, if that makes sense. People see what I'm trying to say about that? It's a very common sort of misconception there. I just wanted to think through quickly. It's okay. All right, so let's just do some algebra. I'll write the next step down, but I was hoping to maybe try or let you guys think about the algebra on this one because it's some good fraction stuff to think about. So when we go ahead and combine those things, we'll get x minus h on the top. We'll get x plus h times x on the bottom, and we still have the h. And so the x's cancel. That's not the confusing part. The next step, sometimes people get a little confused with, right? Because we have a compound fraction. What do we do here? Any thoughts about the correct algebraic approach to simplifying this thing? We've got a fraction divided by a fraction kind of thing.
Couldn't you multiply by h?
You could, can you say more about that? What do you mean by that? Yes, but I'm
Right.
not exactly sure. Yeah.
H over 1.
Yeah, right. So this thing on the bottom is like h over 1. Is that what you were thinking? This right here?
Yeah.
Right. So there's an h over 1 on the bottom. And so we take this and we flip it over and we multiply it by the top, right? And what
Yeah.
ends up happening is it'll end up canceling out the other one. Right, so the h over 1 becomes 1 over h. And then the h's cancel because you have h divided by h. And that's the goal, right? We're trying to get rid of these h's so that we can plug in 0. And we're now ready to do that because enough h's canceled out. I'm gonna need to shrink this down just a tad, run it out of room. And I smooth that h, okay. And so then this becomes the limit as h goes to 0 of just the denominator, which we can do. Let's go ahead and plug 0 in there and we get x plus 0 times x, which is x squared. Oh, and I forgot the minus sign. So this is our derivative. Questions? We don't look at like a ton of algebra, fraction algebra carefully necessarily in this class because it's from past classes and stuff, but I'm happy to look at it more carefully if people would like to. Anything? Is that okay?
So how did you go from the second one on the top there, where you're multiplying 1 over x plus h times x over x, and the other one to that one over there?
So you multiply the tops, right? So like x times 1 is x. And then this minus sign makes them both negative on the other piece. So you have x times 1 is minus x.
Oh,
And then x times, or negative 1 times h is minus h.
okay. Thank you.
Yeah, I did kind of skip a little intermediate step there. Other thoughts about that?
So right next to it, where you flip it, so does that only work when it's 1 over something, or 1 over h, or h over 1?
So that's using the concept of if you have a fraction divided by a fraction, you keep the first fraction and you flip the second fraction. And so in our particular case, I'm sorry, were you going to say something else?
No, it's just, it makes sense now.
Oh, okay. Great. Yeah. So and it was a little bit tricky initially because this wasn't over 1. So we kind of had to recognize it as being over 1 to sort of think about that in that context.
Okay. Yeah, that was what I didn't know how you got the over 1 part. It was.
Yes. Yeah. I was trying to think about a good way to, and there's a couple ways to think about simplifying fractions like that, which is why I was trying to just see what people were thinking if you had one thing in mind. Because the other thing we talk about in my pre-calc classes is like multiplying by h over h or something like that. But anyway, yeah, that's how we're thinking about that one in particular.
Thank you.
Other things.
Can you just explain how you got the bottom part of the original fraction, but like when you went to x minus h? How'd you get the bottom part?
You mean this part right here?
Yeah.
So that was, if we zoom in right here, we're finding a common denominator, right? And that ends up being the common denominator. When you multiply those two things together, you get x times x plus h. So we found a common denominator, which is exactly what I think you were asking about, this right here then, right? So it's like when you add fractions, like 1/2 plus 3/2, you just rewrite the bottom. You don't add the bottom or anything. You just rewrite the bottom, and then you add the top. And that's what we did in that fraction problem.
Okay. Thank you.
All right. Yeah, good questions. Thank you for those questions. The thing I was just going to sort of finish with was, this is our function. This is a function derivative, right? And if we wanted to add a point, it gives us something to plug into. So if we wanted the derivative at 2, for example, or something, whatever, it doesn't matter, any point, we now have something we can just plug 2 into. And so that's nicer than having to do a limit a whole bunch of times if we want points. That's really the only thing I'm trying to say. So if I recall correctly, I think there's one like this in the homework. And so I'm hoping that'll help with that. Okay. Now, in just a second, we're going to throw out all these limit rules. This actually, the way that the homework actually worked out this week is funny, because we're going to do derivatives the hard way, like using the limit. This is definitely the hard way of doing derivatives. And then in the very next section, we simplify it and just make up a bunch of rules so we don't have to do the limit every time. And in the homework this week, we're going to combine, it's going to be a little bit of both. So anyway, before we do that, though, I wanted to give you an example of when this doesn't work, right? So what I'm saying, what I've said, and what we've done a bunch of examples are on these 3 limit definitions are: the derivative exists at this point whenever the limit exists. And so the question might be, does the derivative ever not exist? Which is really a question of, when might a limit not exist? And so I'd just like to do a couple pictures really quick to sort of think about, if we want the derivative to exist at a point. So this is specifically at x equals b, right? So it's at a specific point. Well, in order for that to happen, we need the left-hand limit and the right-hand limit to equal each other. We know that, right? From the right has to equal from the left. That's just the definition of a limit existing. But specifically, we need that to exist with these crazy fraction thing, right? So we need the left hand and the right hand limit with that fraction to exist. And so I'm just going to draw a couple pictures and talk about when that does not happen, right? So when does the right and left hand limit do not exist in that situation? And I'll just remind you that this formula is like the average rate of change formula, right? So it's helpful to maybe think about the average rate of change in these pictures. So, excuse me. One way that this might not work is if both limits exist but are not equal, right? And so, for example, if we have the absolute value of x, specifically at x equals 0, something funky happens in that case. Can I throw a v on here with this? Let me see. What kind of things do you have? No. So if you remember what the absolute value looks like, it just looks like a v. Right? It does this kind of thing. And it creates a 90-degree angle right at 0. And that 90-degree angle is what's known as a corner in the math world. And so if we tried to do if we think about the limit as being the slope of the line at each one of those points, let me just go ahead and zoom in on this one so we can look at it more carefully. The slope of this line is -1, right? Because it's going down. It's just the line y equals -x. And the slope on the other line is 1, the slope here. Maybe I should write slope instead of m in case people are confused by that. right? So it's the slope is -1. The derivative on the left-hand side is -1. The derivative on the right-hand side is +1. And it just switches over right at that corner. There's no gradual change. It just is it's an exact switch. And at 0, neither of those things happen. And so what I'm trying to say, and what the issue in this particular one is if we did the limit as x approaches 0 from the left, we would get this. And that's going to equal -1. And if we did the limit as we approach 0 from the right, we get the same function, except we'll end up with a +1. And the difference is because this thing ends up being negative, right? Because we're approaching from the left. And so since those two things are not equal to each other, the derivative doesn't exist at 0. At the point 0. And it's because of that corner. It's because the corner switches you directly from a slope of -1 to +1 right at that point. Looks like my internet just got a little spotty there. I don't know if you heard me. Do I need to repeat something there? Questions? So this is something that only happens in corners, so absolute value kind of things. It's kind of a special case, but this is something you always see in higher math classes is you can't differentiate absolute values at that corner, specifically at 0 in this case. And so again, that's called a corner. So you might see this in the homework sometimes. It says like, what kind of discount or what kind of why is this not differentiable? And you would say, oh, it has a corner. The other type that we might see where the limit doesn't exist is called a jump discontinuity, which we've seen previously. Remember, that's where the graph jumps. And so something like this, where it's kind of like down here at the point B, and then it just jumps up right here, and we have a jump in the graph. And so the issue there, again, is the left-hand limit is not going to equal the right-hand limit. And so in that case, the derivative at B does not exist. Okay, so the graph, in other words, if the graph has a corner, it won't be differentiable at the corner. If the graph jumps, it's not differentiable at the jump. It's continuous though, right? So let me just add, I'm going to erase this in a second, but I'll just say, note, it is continuous here. So it's continuous at 0, it's just not differentiable. But note here, it's not continuous or differentiable. So trying to carefully think about the definitions here, basically. All righty. We're going to look at a couple other cases where this doesn't exist. So far, I'm just showing you that the right and the left-hand limit of this particular expression might not exist, kind of honing in on the right and the left-hand limit. There's a couple other cases where this might not work, which is potentially the function value doesn't exist. So notice here, you need to plug numbers into this, right? F of B is plugging a number into the function. And so if the function doesn't exist at that number, you can't use that part of the formula, right? And so that might happen if the function's not defined there. For example, 1 over x at x equals 0. We've looked at this one a bunch of times, right? 1 over x does this. And the reason it does this funky thing on either side of 0 is because there's that vertical asymptote. And there's a vertical asymptote because you can't divide by 0. Right? Everyone knows this, I think. And so this is what's called an infinite discontinuity. We've seen this before. And the thing I'm trying to point out if this is the graph of 1 over x, is that you can't plug in 0 in there. So f of 0 doesn't exist. And so if f of 0 doesn't exist, you can't plug f of 0 into the formula. And if we can't plug something into the formula, that means the derivative's not going to exist. If we can't carry out that formula, then we can't calculate the derivative. And again, we've seen this before. Let's just remind ourselves of that word. This is called an infinite discontinuity. Right, just because it goes to infinity at that location. Questions about what I'm trying to say there? Okie dokie. The other type that doesn't exist is a very special type where the limit as x approaches a at that location doesn't exist. And so I'm just going to explain this one with a graph that kind of looks sort of like a V again, except it does this thing called a cusp. So this location right there is called a cusp. And it's different than a V because it doesn't, for one thing, doesn't make a 90-degree angle. What it's doing is it kind of comes and curves down and then quickly curves the other way. And so if we think about the derivative as being the slope of the tangent line, let's remind ourselves. F prime of b is slope of the tangent line, right? Let's draw a couple tangent lines on this thing as we get close to the cusp. So the tangent line right here, let's just pretend that has a slope of, I don't know, -1 or something, right? It's negative, it's going down. As we get closer to 0, notice that the slope of this thing gets almost vertical. Like this is basically a vertical line at that cusp point. What's the slope of a vertical line?
0.
Have a slope. Sorry? So I think you said 0. If we had a horizontal line, the slope is 0. If we have a vertical line, the slope is like infinity or something, right? It's like you rise infinity and you move over 0. So it's like infinity over 0 or something, right? That's not a sensical, that's a nonsensical expression, infinity over 0. And so at that cusp point, you end up with a vertical tangent line, which is showing us that we don't have a derivative there because you get a nonsensical slope. And so I'm going to erase some of this. I'm just trying to, all the blue is just trying to explain the concept, and I'm going to write it down in words in a second. If you want to write that down, go ahead, but I'm going to write it down mathematically and using some words. Let me clear up that picture a little bit. Maybe I can redo this a little bit. Slope of the tangent line, so that's good to keep. And let's add a couple more words there. So what I'm trying to say here is at x equals 0 in this particular picture, if we tried to look at the limit as x goes to 0, so we tried to calculate the slope of the tangent line, we would end up with infinity, or infinity over 0, which is even worse, right? And the reason for that is because there's a vertical tangent line at 0. So if there's a vertical tangent line, i.e. a slopeless tangent line in some sense, then you can't have a derivative there, right? What's the numeric value for infinity? There isn't one. And so the derivative at 0 here does not exist. I'll just say because the limit does not exist. Again, this is specific kind of function that has a cusp and is a very weird special case functions that, to be perfectly honest with you, I have never seen in practice. And when I try to look up what the functions represent, they're funky looking, and they're the kind of things that are very special cases. And so in other words, it's not the kind of thing that you might see. Like you would definitely see 1 over x in practice. You would definitely see absolute value in practice and piecewise functions. Like the previous 3 happen frequently. Cusps don't happen too much, but it illustrates a concept, right? It illustrates a concept of when this limit might not exist. That's what I'm going for. All right. Can I clarify anything about that? Okay, I would really like to look at some of this homework. Like I can't emphasize enough how I think important it'll be for everyone to look at the homework before Wednesday and come in either with some questions or at least an understanding of what other people's questions will be. That's how you're going to be do a nice job on that homework, I'd say, because this stuff is tricky. You're doing limits. You're trying to understand this weird notation that you may not be familiar with, and so it's tricky. Let me know if I can help. As we move forward, though, let me just pause again and see if there are questions before we keep going, because what we're going to do in a second, as you can see, is we're just going to come up with a bunch of rules and not look at the limit anymore. The limit is the conceptual part of the derivative. And if you've taken calculus in high school before, you might not really get into that limit derivative very much, or the limit definition. We really kind of emphasize in college because we're trying to, have a deep understanding of this stuff. But what the next page sort of says, and you can just see what it says right here. We learned how to calculate the derivative using this function or the other ones. But these things, you can use this to derive the below rules. And so instead of having to do a limit every time, right, we just know that we can just follow these rules because these rules follow from this limit definition. That's what I'm trying to say. Let's see here. Do we do reactions? We do. I'm just curious, how many people took some version of calculus before in high school or some other time where they're kind of familiar with, for example, the power rule? Is anyone familiar with any of this stuff? And if you are, maybe just raise your hand or put a thumbs up or something. See how I'm doing that in the chat? I'm just curious if this is brand new to some people or everyone, or if there's a couple people seen. Okay, great. Only maybe a couple people have thumbs up. Wonderful. So if you are, great. Now we're getting into something that maybe you're familiar with. And I'll just say again, if you're not familiar with this limit definition, it's just because a lot of times in high school we don't go in deep into that. I recall in high school, it's like the kind of thing that your teacher kind of shows you. Maybe you did an example, but it's not the kind of thing that you might see in homework and things. And here we're doing it in the homework, and then we're moving past it into this stuff. Okay. So, and some of the homework this week is based on this stuff. So I'm probably going to fill out the rest of the period here with a few of these rules. So notice there's a lot of them, right? There's a couple of pages of them. This is the kind of thing that you want to have sort of out and reference. And paging through people's notes, it looked like almost everyone printed the notes out, which is great. And what I would suggest is this particular page, does it fall on, I hope it's not between pages or not. But anyway, you might just want to have this sort of out separate from your notes as a reference. I always come back and reference this page, or I'll try to at least. And it's a good idea if you had it referenceable too. And again, the idea is we apply the limit definition and we get these rules. So for example, and let me sort of set up the page. So on this page, all these things are constants. So C, B, M, N, A. Like here's a C, here's an A, right? Here's some of the other ones. Here's another C, here's an M. All those things are just constants. And so the only thing that's a variable in here are the X's. And what's going on here is it tells us the form of the function in the middle column, and then it tells us the derivative in the right column, right? So notice how here we have f of x and here we have f prime. And so the right-hand side is the derivative of that one. And so what the first one tells us, this is the most basic rule there is. This is what the homework's on this week. It's the power rule. It tells us when we have x raised to the power of n, when we take the derivative, You just bring down the power n and subtract 1 off the power. See how that's what that says? Let's do a quick example of that. If our function is, for example, x squared, like we just looked at previously, we found that the derivative of that was 2x. And here, what we're seeing is that rule in practice, right? The derivative is bring down the power, subtract 1 off the power. That's what this rule tells us to do. And so we get 2x, just like we found previously, right? We just did that a second ago up top, and I think it's worth at least kind of sliding back up to that right here, right? We just did that right here using the ugly limit definition. It was a whole bunch of work, and what I'm saying is, hey, we have a rule for that now. We don't have to do the limit definition anymore. We can just use the power rule if we want to do something like that. We just bring down the power, subtract 1 off the power. Right, and there's a little 1 right there technically. Is that okay? See what I'm saying there?
I follow what you did, but like, what's the point of that? That's the.
Let me put my hand down. The point is, if we want to take the derivative of something raised to a power, like this one, right? This is an example. This one right here was an example of a function raised to a power, x squared. And we did all this work with a limit, and we got 2x. And what I'm saying now is we don't have to do the limit definition anymore. We just know we bring down the power and subtract 1 off the power, right? So if we had x squared plus 1, it turns into 2x without doing all this intermediate stuff.
Cool.
Right. And we did the example, right? We did that one here. And so hopefully you saw how that worked out the hard way. And I'm just sort of saying, okay, we did it the hard way. Now here's the secret rule that we can use without and to avoid that stuff. And the weird thing is in the homework this week, you're going to do both of them. You're going to like struggle through doing it the hard way, and then you're also going to do it the easy way. Sorry, what was someone going to ask?
I was just gonna ask a quick question. On the example we looked at, it was x squared plus 1. Does it matter what the b is, what the plus b is, or minus?
Yeah, good question. So that's actually the second rule here. Let's jump right into that. So that's the constant rule. So if the second one says if we have a function that's just a constant number, when you take the derivative, you just get 0. And so in the example we just saw, and leave a little gap there because I want to do another example of that other one, the power rule. So if we had the function 1, that's just a constant, right? This is telling us when we take the derivative, it becomes 0. And so that's why in that previous one, that's why I wasn't trying to harp on that because I wanted to say this first. In the previous one, the 1 just went away because it just became 0. And that should make sense. If we think about this as the slope of the tangent line, right? A constant function is just a horizontal line. Right, there's the function 1. The slope of that line is 0 everywhere. And so that's what this is telling us. Right, if we have a horizontal line, the slope is 0. That's literally what f being constant and f prime being 0 means. I feel, is that helpful? Maybe I'm gonna write that down. So let me just say the slope of a constant function is 0. That's what this rule is telling us. Is it okay? All right, I just wanted to do one other power rule example to show you how that comes up sometimes. Do I have enough rule to sneak it in there? I think I do. You might want to write it somewhere else. Sorry if you don't have enough room right here. So it comes up, let's do another power rule one. When we have radicals or this is not going to be enough room, is it? If I write small, I'll be able to fit it in here. I apologize. You might need to fit it in somewhere else. Let's say we had the function. I'm also skipping ahead a little bit. Where's the sum rule? Yeah, the sum rule. Okay, so real quick, one of the questions that Josh had asked was what happened with the x squared and the plus 1. So those are two separate things, and I just want to point out that that was the sum rule. So let me just talk about that real quick. This says when you have two separate things being added and you want to do the derivative, you just look at their individual derivatives. Right? So the example we just looked at for that would be like this. That x squared plus 1. Right? If you want to do the derivative, and let me remind you of this notation. If you want to take the derivative of the function, you just take the derivative of each of those pieces. And when we take the derivative, we get f prime. And so this is just an application of the sum rule, because we had two separate things being added, and what the sum rule says is you can just look at them separately. And when we looked at them separately, one was a power rule and one was a constant rule. Could mention one other thing. There are questions about that. I'm going to slide up in just a second. Maybe we should talk about, let's do the linear function one too, because that's an application of both these things, right? So let's pretend we had f of x is, I don't know, 2x plus 8. It's a straight line with slope of 2. What this says is the derivative is 2, right? It just tells us that whatever the slope is, you get that as the derivative. Could someone explain why that makes sense? Practically speaking, why is it that the derivative of a line is just the slope?
This is going to stay the same
Because
regardless.
Yeah, that's right. So, and who else was going to follow up with that?
I was just gonna say because on a linear function, like on a straight line, the slope is always the same.
Yeah, exactly. If we looked at 2x plus 8 is something like this, no matter where we look at the tangent line is the line itself, right? If I was going to draw a tangent line, let me do it another color. It's just going to be right over top of the same line because it's just a line, right? And so a way to think about that is like the slope is how the line is changing. It tells you how the line is changing, and it's always changing at that same way because it's just straight, right? But the other thing I was going to point out is this is an application of a couple different rules. So if you took the derivative of mx plus b, you take the derivative of mx and b separately. That's the sum rule, right? Mx is a power rule. We got the constant rule in there with b. And so you can see how that we start putting rules together, basically, is what we're trying to do. These snowball, and you just look at each individual piece is what the idea is, and you combine all these different rules together. Questions so far? Slope is how is line. Slope is how lines changing. You guys are gonna let me get away with that? No one's gonna say anything? Like,
I was
yeah.
just looking at it just now, and I was like, "What?"
Slope is how lines change. Let me try that again. Slopes describe how lines change. How's that? Man, sometimes I feel like, yeah, they're on it, they're asking questions, and then like other times I write something that doesn't make any sense, and you just let me write it. No, I'm just kidding. Okay, so I just want to do one more power rule example. That's where we were. So what if we had something like this? 1 over x times square root of x. We can think about that as a power rule by thinking about that as x to the minus 1. I'm sorry, put a plus in between there. That's what I meant to do. plus x to the 1/2. Right? 1 over x doesn't look like a power rule, but when you write it as x to the -1, it does look like a power rule. Right now, they both look like this. They both are kind of in that general form. Square root of x doesn't look like that, but when you write it as x to the 1/2, it does. And now we can apply the power rule just by kind of thinking about that a little bit differently. Right? And when we do it like that, the derivative ends up being bring down the power, subtract 1 off the power. Bring down the power, subtract 1 off the power. I'm sorry that got a little jumbled there. Hope you had somewhere to put this with a little more room. What I'm trying to point out is 1 over x's or 1 over x raised to a power or radicals you can think of as power rules. There's more complicated ways to do them, right? We just did 1 over x in a very complicated way right here. We just did this one a second ago. Here we were doing 1 over x the hard way, and we had to do fractions. We did the limit, blah, 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 blah. What I'm saying is, let's just think about that as a power rule and make our lives easier. Do people see how that power rule went, though? I didn't do the details because I was running out of room, but I brought down the power, multiplied it, and then subtracted 1 off the power. Is that okay? Good. All right, we're gonna end with the power rule. We're gonna kind of slowly go through these over the next several classes, 2 or 3 classes. The thing I'm gonna ask you to do on Wednesday is the power rule. Okay, there's gonna be homework in Wednesday that relates to the power rule. And so just know that this stuff is gonna be in there. And what I'd like to just finish class with are the 3 examples that use the power rule. Right, so you can see the next couple pages are kind of broke down by different types and whatever. And let's just finish off with some power rule examples. Maybe I'll think about a couple and then ask you to think about a couple. So, super easy ones like this, polynomials. They always use the power rule. Right, because they're just x's raised to whole powers, and so we're going to use that power rule. The one that I've kind of skipped over so far that we should hone in on is the constant multiple rule. So let me just slide up real quick and show you this one real quick. This constant multiple rule, have we done it already? Not really. Can you guys hear my dog in the background, or is that just me?
Very faintly.
Okay, good.
Dog is very loud.
Super distracting for me. Let's see here. We're almost there. With the constant multiple, it's just telling us if we have a constant times a function and we take the derivative, we just ignore the constant and we take the derivative of the function. Do you see how that's showing that here? It says like C doesn't change. What changes is G turns into the derivative. Right? So you just kind of like ignore the constant and you just work on the function. And so that applies here, because if you had something like this and you take the derivative, you ignore the number and you just focus on the x cubed is what I'm sort of saying. I'm going to erase this in a second because I don't know if I have enough room for that, but I'll kind of show some of the details here. Right, so something as simple as a polynomial like this one actually involves a bunch of the rules up there. It involves, we're going to use the power rule because they're all raised to powers. We're going to use the constant rule because they have some constants in front of them. We're going to use the multiple rule. And the sum rule. So a bunch of things come into play, and it's not hard stuff. If you've never seen this before, it's maybe does seem. But what I'd like to sort of preview in the future is this stuff should become kind of second nature, and it's not terribly difficult. It's easier than doing the limit, that's for sure. All right, so let's do this one. So when we take the derivative we bring down the power, and we subtract 1 off the power. I'm going to do this one kind of carefully. Notice how the 16, right? This is one people get confused about. It's 16 times x to the 1. And so you bring down the 1 and then subtract 1 off the power, and then you end up with x to the 0. And then when you take the derivative of 9, it just becomes 0 because that's the constant rule. And so let's keep simplifying it and let me know if this looks okay. This becomes 4x cubed, 6x squared, 16x to the 0. What is anything raised to the 0?
One.
Number 1. And so the thing that we really want to take away from this is when you take the derivative of x, it becomes 1. That's something that people get confused on, right? So this is 4x cubed plus 6x squared minus 16. That's the final derivative. And the thing one of the things I'm trying to point out here is when you take the derivative of x, you just get the number 1. Not 0. Oftentimes people think you get 0 when you take the derivative of x. You bring down the power, which is 1. You get x raised to the 0, which is 1. So it's like, oops, sorry. It's just 1 times 1, which is just 1. Right? Maybe even let me write the details. You have 1x to the 0, which is 1 times 1, which is 1. Right? And is everyone okay with this notation? This d over dx? I mentioned it last class, but I haven't mentioned it again. Maybe I'll just slide up and point out to you where that says it. It says it right here. Right here, all the different ways that we can say take the derivative. And one of them is d over dx. And I wrote that right there, right? D over dx means take the derivative with respect to x. So that's a notation I'll use when I'm doing like, hey, I'm about to take the derivative of this, and then the next step will show the derivative, right? That's right. We're trying to think about this like writing a book almost. So I'm saying when I write down something like this, I'm saying I'm going to take the derivative of x, and then the next step is I did it. Okay. Thoughts about the power rule on that one? Does that seem okay? Okay. I think I'm going to stop here. I think this one will be a good one to start with next time, and then I'll let you try the last one. So I'll sort of refresh your memory with that first one, and then I'll let you try the second one, and then we'll start digging into some more rules. Questions about anything? There is a minute left. I'm happy to stick around if you've got some homework questions or anything about the notes you want to chat about. Anything about anything here? All right, cool. Well, we'll start with that next time. And let me know if you need anything in the meantime. Remember, I've got office hours over the next 3 days, so pop on in if you want to chat about this stuff. Love to do that. Have a good one.
Thank you, Professor.
Thank you.